Hi, IB Physics exam is approaching, and we all know that the data booklet is very useful during the exam. However, in the past I find out some of my students didn't utilize the data booklet and they didn't prepare themselves to use the data booklet properly in the exam. So in this video, I'll aim to do 4 things. As you can see here, the first thing is I'll try to go through each symbol with you. And in fact, you may find this file on the internet if you simply search Physics Data Booklet annotated. And thanks to this person, sorry I don't know how to pronounce your name, but then you can see that in the later part, most of the symbols are annotated already. However, with due all the respect, some of the annotation is not completely correct. So I'll try to point out something you need to pay attention. And number 2, it's also important when you study physics to realize that some equation would need assumption, otherwise they would not be valid, and that means you cannot apply them. Or in certain case, the exam question may ask you what are the assumptions or why the equation cannot be applied in the actual situation. So knowing this will be very useful. Number 3 is there are some equations that may be useful for your IB exam, but they did not appear on the booklet. So I'll try to add it in when we cover each chapter. And lastly, I'll also talk about some misconceptions that I find in the past. Notice that this video only covers the core topics, that means topic 1 to 8 only. For HL topics, if you find this video useful, you can let me know and I will think about making a similar one for the HL topics next year. Topic 1. You may find the equation for uncertainties here, and you may recall that, hey, paper 3 is actually cancelled this year and also next year as well. So probably you think, oh, I don't have to study this. Then you're wrong, because this may still appear in paper 1 and you may still need to use this equation. So the first thing that you need to know is that this equation is for adding and subtracting, and the equation here is for multiplying or dividing. So if you don't know how to use it, then you can refer back to my chapter 1's video. I can put the link in the description below. And the annotation here is all good. And you can also interpret this as percentage error, because this is delta, that means the uncertainty over the average. So in fact, I will probably put down y log, a log, b log, and c log, because this would mean the average value. So the misconception that I find, and also the exam would like to kind of trap you, is you have to make sure why this quantity is the main term. So in a case where they may tell you, oh, say x equal to y, z, and say over k, but then they want you to find out, oh, this is being considered, and try to look at how many percentage error it is, while this is being measured for z, and also k is being measured and x is also being measured, and they want to find out why these values is uncertainty. So in this case, what you have to do is you have to rearrange it so that why this thing will be the main term. So what you want to find and calculate will be the main term. So well, obviously you should know how to do it. So after you get this, then you can apply the equation. Well, here you may find, oh, well, there's no difference. If you try to think about how you add them up together, there is definitely a difference. So knowing what is being measured and which one is being calculated is very important. 1.3 is nothing special because it's simply mathematics. So if you still struggle the component, like this is taking cosine while this one is taking sine, then good luck to your exam, because I don't think you should refer to this. You should know it directly without seeing this. Topics 2.1. Here you got 4 kinematics equation, and in fact in physics there's a 5th one, but these 4 will be sufficient enough for your IB physics. And I'm sure you all know the symbol for these 5 quantities. And I would say for acceleration, you really don't have to know it is g for gravitational, because it really depends on situation, because a could be 0. Maybe if you're looking into projectile motion, then usually when there's no air resistance and horizontally a is 0, and vertically a will be taken as g simply. However, one assumption that you must know is that whenever you use this equation, no matter which one, then you have to ensure that a, acceleration, must be a constant. Okay, that means it cannot be changing throughout the motion. And that is why usually the questions will say, oh, neglect the air resistance, because in that case you cannot use this kinematics equation, since for air resistance it will be changing throughout the motion and therefore affecting the acceleration. Topics 2.2, F equals ma, obviously everyone will know what it is. However, these also have an assumption, although it doesn't really get to mention in IB much, and that is m mass is constant. Alright, again, this equation is valid only when m is constant. In the case where m is changing, for example, when you're having a rocket motion, because the fuel is burning, right, or is propelling some of its mass backward, so then m is not constant, and therefore the equation cannot be used directly, unless you are just calculating the instantaneous acceleration. The other 2 equations is about friction, and obviously one is about static, that means it's not moving. Dynamic means when the object is moving already. So I wouldn't say anything that is too special. I would rather say something that you should probably memorize, alright, as in the new equation in this data booklet. That is, for the inclined plane, when you have an object on this plane, and let's say the mass is m, okay, and I guess you know what I'm trying to say. The weight, right, will be downward, but then you can always decompose it in 2 directions. One is along the plank, and for this one you should, and I would recommend you to memorize it, that is W or mg sine theta if this is theta, and while the one that is perpendicular to the plane will be W cosine theta. And normally W cosine theta, this one will be of the same magnitude of the reaction force usually, unless someone exert another force like in this direction, but then that's very rare. Yeah, so I would say you should memorize these 2 and it will be very useful. Topics 2.3, the first one is work done equals to force times distance in the same direction. So that's why you need to take the cosine theta if they are not in the same direction. But I would say do not bind with cosine, because it may be sine theta. It really depends on what angle it is. For example, if the box is like this, and let's say here's a tension moving the box forward, and it really depends on which angle you're talking about. For example, if this is theta, then yes, that's fine, right? T cosine theta will be the one that is going horizontal. However, if you're talking about an angle that is in this direction, then this equation should be changed into sine theta instead. And just by the way, I think work done is something that you should definitely know the detailed definition you can find in the textbook. I'm not going to cover those things in this video. Next is kinetic energy equals to half mass times velocity squared. Nothing really special. You just have to make sure that the SI units should match, so that energy units will be joule. For the next one, something that you should pay attention is the unit of K, which is spring constant, and X, extension, because sometimes they may not be matching. For example, spring constant that they gave you could be Newton per meter, while the extension they give you could be cm, so you may need to do the conversion there. Another thing that you should pay attention to is sometimes the spring may not be extending from equilibrium. So, well, let's say normally you have a spring and that is say 5 cm, and now you extend it further to say 3 cm more. Okay, and so doing this equation, calculating would be very simple. You just substitute 3 into this and square and then multiply the other things. But then there are times where they may ask you, oh, what if I now 3 cm and then I extend 2 cm further? Okay, and so when you are calculating the energy you need for this extension, it will be different. All right, you don't just substitute 2 into this, and you also don't substitute 3 minus 2 square like this. You don't do this, and I feel this delta x is a little bit misleading. All right, so just make sure you're aware of that. So the actual way that you should do is to simply calculate the energy you need to go from here to 3 cm. That's using half kx squared simply, and try again to calculate from equilibrium to whatever you want. So like here, so that is the extension to be 5 cm in total, and after that you minus them, and then you can find the energy at this point. The purpose of doing this is simply mathematically 3 minus 2 square does not equal to 3 square minus 2 square. This actually is simply the main issue, or you could also see it as 5, because in total this is 5, right? 5 minus 3 squared does not equal to 5 square minus 3 square. So I would recommend, to be safe in exam, you want to do it separately, and then you minus the whole value of energy to find the difference if necessary. If you're starting from natural length, then no worries. I mean, you start with 0 potential, so it will be very simple. For GPE, it simply is mass gravitational acceleration times the height difference. So for this one, it's really just use the height difference and find out the GPE change. So nothing special. For powered, first of all, this is not the definition. Okay, this is a derived equation. If you're looking for definition, P equals to energy over time. This is always the most fundamental definition of power. As for force times velocity, you need to know that there's assumption. And the assumption is that if you are only using P equals to Fv, then you have to make sure that the force and the velocity has to be in the same direction. Because if they don't, then you have to also take an angle, just like how you derive the equation of work done, because that is simply where the equation came from. So in fact, if you could, I would suggest you to start from the fundamental, so energy over time, instead of using this equation F times V. If you really have to use this, then you should make sure if F times F and V are in the same direction, and also whether or not they are changing throughout the time during the motion. It would be better if they don't. For efficiency, just to make sure that you only multiply that percentage with energy or power. So usually the question may give you maybe the efficiency, and you can use it to maybe calculate the useful one. One misconception that I recently find is that my student, for some reason, they thought you can also multiply efficiency to other physical quantity, for example, voltage or current or any other thing. So again, make sure you can only multiply the efficiency to these two only, energy or power. And lastly, of course, in this topic, one equation that you would definitely need to know, or more like a principle, is conservation of energy. And I don't think I should write an equation here, but then this is one of the very basic principle you need to construct the equation using these, of course. And 2.4, P equals to mv, momentum, nothing really special. You just to make sure that you know momentum is a vector, and so when you are calculating it, you want to make sure you consider the direction. While for energy, they are scalar, so you don't have to worry about those. Next equation is delta P over delta T equals to F, and I would like to point out that F is resultant force. That means net force, in other words. You may wonder why. Why do we have to point this out? Is that normally it's okay, like if you are doing a horizontal motion. However, if you're doing a vertical motion, okay, then it will be different, because for example, if the ball is changing its direction, right, when it bounces and touch to the ground and bounce back up, then there are different forces involved. First of all, you have weight, and next you have reaction force, and so these two combined all together will become the net force, and that is the change that you're going to make to the ball so that it can go back up. So not just one force, but all the forces that you are acting during the impact. While delta T, more precisely, should be the impact time. For the next equation, that is kinetic energy equals to momentum squared over 2m. For this equation, you may not use it often, but then in a case where when you see a question mention these two, kinetic energy and momentum, sometimes it may be useful. So you can think about it, I would say. Yeah, but then nothing really special, because this can simply be derived from the kinetic equation and also the momentum itself. So if you just rely on these two equations, it should still work, but then it may take you longer time if somehow this equation can fit to the question. And number 4, you can see, I don't know why they have to put this, because this is basically the same as number 2. You just have to rearrange the delta T to multiply F, and finding out delta P, changing momentum, we call it impulse, right? Which is, just by the way, because I don't want to mention this every time, for other topics, is the area under the curve. However, there is one equation that definitely you should not forget for this topic, and that is conservation of momentum. And the equation is usually, I said, mu plus mu equals to mv plus mv when you have two objects that collide or they get explode from the same object. So 1 1 2 2 1 1 2 2. Okay, and I'm sure you have seen this equation before. However, I'm not sure if you are aware of the assumption. The assumption of this equation is no external force. Alright, this is important when we derive this equation, and that means if there is other external force which could be friction, then you should not be applying this equation. Before we move on to chapter 3, I would just like to remind you a special type of question in momentum, and that is a question involving the mass at a certain rate. So this is an example, and one key trick that you may need is simply using the same equation, delta P over delta T equals to net force, but then you kind of have to rearrange the equation so that you have delta M over delta T, so then this will be the rate of the mass. So if you are interested to know more about this, then you can also refer to another video of mine in chapter 2. Topic 3.1. So these two equations, for sure you are quite familiar with that. That is energy equals to mass times specific heat capacity. And just to remind you that the unit, right, by looking at the equation, actually you can tell it's joule per kg per k. Okay, make sure you write the slash here as well, or you can put a bracket, right, to contain them. Do not put something like this, because this is ambiguous. Okay, don't do that. And for delta T, you should be aware of the unit that is applicable to both degrees Celsius or K. You don't have to convert them. So in exam, I recommend you don't do the conversion, because the more step you do, then the more mistake that you may make. The lower one is simply energy equals to mass times the specific latent heat. So that will be in the units of joule per kg. So obviously this is when you are changing a temperature, right? Good description here. And the next one is changing its phase. The other equation that you get to link quite often is the equation of power, right? It goes to energy over time. So maybe there are times where you have a graph, then you may want to use the power given, multiply the delta T, and you can find the energy supplied during that period. More importantly, another equation set that you may get to use is based on, again, the principle of conservation of energy. So what you may want to write is firstly saying that energy gained by something will equal to energy lost by something, and maybe they are mixed together. They are allowed to exchange the thermal energy until they reach equilibrium. So in that case, you would need to think about this equation, or maybe sometimes also consider the latent heat. That means both of them. But let's say if you only consider the first one, then usually the equation should look something like this: mc and then tf minus t of that object, so 1 1 1. Okay, so let's say this is the first object, and then you have another object that is m2 c2, and then this is t2 minus T final. So like T final is a temperature that is between T2 and T1, and let's say T2 is somehow hotter, so apparently this is going to be lower temperature, while T1 is colder, like of a lower temperature simply. And so this is how you could construct the equation. Before we start 3.2, I just want to remind you another relevant concept that is called the molar mass. So you may see this in the question, and you should recall that this is something to do with the element, how many gram per mole. We must use gram. And the number usually depends on how many atomic or the nucleon number, I should say, it has. So for example, carbon is 6 proton and 6 neutron, because we usually say carbon 12, so it's going to be 12 gram per mole for carbon. So the first equation you encounter is pressure equals to force over area. You may also know that it could be delta P. So for example, if you say have a door and there are two different pressure, P1 and P2, and so there's a pressure difference, and therefore they would be exerting a force to a certain direction. So let's say P1 is stronger, then this will exert a force, and so that could be calculated using this equation, F over A. The next one is probably very useful, and you want to know and memorize by seeing whether this is small n and big N. Okay, this is how I usually phrase it. Well, I know this is called lowercase and capitalize, but then I think calling them small n and big N would just be easier. So this is describing how many mole you have for a certain substance. So for example, if you have 2 mole, it will actually means that, because this is Avogadro constant, as you can see here, which is a constant that you can find from the earlier page, which is right here, right? 6.02 times 10 to the power of 23, and you can see the unit is per mole, and therefore that would mean you have roughly 6.04. Sorry, 12.04 times 10 to the power of 23 numbers of substance. So obviously this number is much bigger, and that's why it's called big N, and while 2 mole, 2 is much smaller, so that's why it's called small n. And so that would remind you that during the ideal gas law, this N is for mole only, not the total number of the molecules. As for ideal gas law, PV equals nRT, pressure times volume equals to numbers of mole times gas constant times the temperature. Something you need to pay attention is, first of all, T has to be in Kelvin. For this one, you can never use degree Celsius, never. Okay, and converting that, it shouldn't be hard for you. It's just a difference of 273, converting from degree Celsius to K. So you should know whether it's adding or minus. The next thing about ideal gas law is you could be having something being constant here. So you need to be very careful with the question and try to read carefully. So for example, when P is constant, pressure is constant, then you will get something like V over nRT. Okay, if I just rearrange them to one side, or you can do the other way around, it doesn't really matter. nRT over V will equal to nRT over V. 1 1 1 1 2 2 2 2, and of course, I mean, this is a constant, so I don't even need to put it like that. And so that means the rest should be of this sort of ratio. If pressure is constant but some other things got changed, for example volume change, and maybe temperature will get to change as well. And you will need to see if it depends or not, whether there's new molecules taking in or they are leaking. So that would be the same when you have T to be constant and V to be constant. You should be able to deduce something like that. And the other thing that you may get to use and somehow underappreciated when dealing with ideal gas law or some sort of gas exam question is the idea of conservation of mass. Okay, this is somehow underappreciated. So due to conservation of mass, then you should have N1 equals to N2, or like total number to be equal. Sometimes you may need to have, say, 2 chamber, okay, N1, N2, and somehow they'll say, oh, the valve got open and mixed up, and so what you have to do is to find out maybe N1 plus N2 equals to the total N that you have. So let's say N3 at the end when you construct each equation for this ideal gas law. The last equation in 3.2 is about average kinetic energy, because you can see the bar at the top. In fact, when you talk about average kinetic energy, we shouldn't be saying this word per molecule. So I mean, when we talk about average, it's already per molecule already. Think about this. All right, I always tell this to my student. When we say average height in our class, so it might be a number that is it's just a random number, 171 cm, let's say. Okay, so that will mean the height, if you randomly pick someone, it should be close to this height. All right, so this should be sensible. That is a ordinary person or maybe an ordinary classmate height. It would never be the total when you talk about average. And obviously, if you want to find total, you need to multiply the number, because that's how you calculate average. You add, let's say there are 10 students, you add from 1, 2, 3, 4, 5 to 10, add together, divide by 10. So if you want to find the total, somehow total height, I mean, it's not really meaningful, but then let's say if you want to find it, you have to multiply 10. And so here, if you want to find total kinetic energy, and it does, sometimes it may really ask you, then what you will need to think about, okay, sorry, I'm running out of space, maybe I'll copy here, is you simply multiply the big N, okay, because big N represents how many literally of particles you have. So you have something like kinetic energy total, or sometimes the textbook will say U, as in total kinetic energy. That will be 3 over, I mean, just copy it, but multiply the big N. And then for the right hand side, you can see more precisely that's n over na, Avogadro constant, times RT, and in fact this is simply the small n, which is the mole number. So that means the total energy can be expressed as 3 over 2 nRT, and that means it can also be expressed as 3 over 2 nRT equals to PV, right? So it can also be expressed like that. Again, remember this is total. And just to remind you that KB is the Boltzmann's constant, which you should be able to find in the earlier page right here. Moving on to topics 4.1, this one is very simple, period equal to 1 over frequency. However, the more important equation that you should recall, and I don't know why it doesn't appear here, is the definition of SHM, and that is having acceleration proportional to negative x. This definitely is something you must recall for topics 4.1. For 4.2, it will simply be the wave equation V equals to F lambda. I usually write it this way. C here, I guess is referring to speed of light, but in fact, you can use it for any sort of velocity, for any waves. Just one thing that you may want to be alert is that sometimes you don't use this. Sometimes they will say, oh, there's a wave, alright, travel for a certain time, and then they want you to find a certain distance. In fact, you may just simply use velocity or speed equals to distance over time, simply. So for example, they say, oh, there's a radial wave sending out, alright, for like whatever millisecond, and then to find out how many distance that it go through. So you may just simply say, oh, distance equals to the speed multiplies time, and so you can just substitute the speed of light into it. Topics 4.3. So I think these are all self-explanatory. Intensity proportional to amplitude square. Okay, so that means if you are comparing the two sources, or somehow they say, oh, now the amplitude is double, then intensity will be 4 times bigger, because if it is A twice, then with square, then it will give you 4i of the original. So this is something that usually that would be asked. While for the second one, it's actually referring to the point where you're measuring that intensity, because usually it will radiate out, right, in all direction, and that will make a sphere. And in fact, intensity equals to power over area. So not to confuse this A with this A, this is amplitude and this is area of the sphere. So we would be able to phrase it as I equals to P over 4 pi r squared. And so that is r of the distance that you travel, and that's why it is x negative 2, right? Because here is r squared, all right, inverse, and that is the reason. And that obviously explains why if you're further away from the light, it will look dimmer to you. The next one is the one that you use for polarizer. So I don't think you will use it wrong, because this is the only use, right? The so-called the Malus law. The only thing that you need to pay attention is I log is the original intensity, and while angle is the angle between the polarizer. Okay, not to the normal or whatsoever, it's between the two polarizer. So something interesting may happen when you have 3 polarizer. Maybe one is completely horizontal, one is vertical, and one is like in a certain angle. Normally, without this, you see nothing at the end, right? But then when you add something like this, you see something more. So this is a question that we discussed when it is back to 4.3. But anyway, when I say applying this, I would recommend you to think about the intensity with a certain name, use a notation. So maybe when you're going in is I log or I0, and this is I1, I2, I3. And so when you're applying here, then you have to look at the angle between these two polarizer. Alright, and then you can lay out the equation that is I3 equals to I2 cosine square theta. Okay, so you can apply on whenever you pass through a polarizer. Something not related to the equation, but then I will still like to remind you is you need to pay attention to the incoming light, whether or not it's polarized or unpolarized, because that will make a difference. If it is polarized, then you have to think about the angle. If it is unpolarized, that means it go in all direction. And after it passed through the first polarizer, it will simply be divided by 2 of the original. So reading and knowing whether it's polarized or unpolarized is very important. Topics 4.4, we all know this is Snell's law. Okay, you have done this a lot in IGCSE. However, sometimes we may get to use these two to pair up. So the ratio of refractive index is the inverse of the ratio of the velocity, or sometimes we may do it this way. Okay, so you should be able to identify what the questions provide and what they are trying to ask. The next one is about double slit, and so if you simply recall the idea of double slit experiment, you probably would be shining the laser to it, to double slit, and for a very far distance, because you want to see an obvious pattern, then probably it's like 3 meters, so really far, and then you'll be able to see the interference pattern, something like the brightest in the middle, and then dark fringe, bright fringe, dark fringe, bright fringe, etc. And so for this equation, S is the fringe separation or spacing. I usually call it separation, and that is defined as between each, so bright to the consecutive bright fringe, the distance between them. So this one you surely would not mix it up. Lambda is simply wavelength, very obvious, and so the one that you may mix up is the D at the top and the D at the bottom. So I'll call it big D and small d. So big D obviously is the one that is longer, big D, and while small d is smaller, of course, right? So that is going to be the slit spacing instead. So this probably will be a certain micrometer or even nanometer. So it will be so much smaller than the screen separation. For the next one is about the interference. So path difference, in case you don't remember, is calculated from, let's say this is point A and this is point B, and if you want to find a certain point, let's say this is a point of C, which you have the interference, no matter it's constructive, destructive, or whatever. If you simply just want to find the path difference, what you are going to do is to draw a straight line from A to C and draw another line from B to C, and the distance of these two minus will be the path difference. So that means path difference in this case will be AC, okay, the distance of this, minus BC. Okay, I put absolute value because we just want to know the positive value of the distance. And so I'm sure you should know how to use this equation. And just to remind you, one misconception or one mistake that people usually make is for destructive interference, some people may do something like and lambda over 2 instead, right? I mean, if you refer to this equation in the data booklet, you wouldn't make such a mistake, okay? Because this is stupid. This is referring to basically 0.5, 1, 1.5, 2.0, 2.5, etc. Basically all sort of interference. So you should never use this expression n lambda over 2. You should either use n lambda or n plus half lambda instead. In fact, when you try to use this pair of equation, there is assumption here also. Okay, although from what I see in IB, usually it is okay, right? Usually that means you don't have to worry about this. But then just to understand better, you should find the two sources, for example A and B here, they have to be coherent. Coherence means when A send out the wave, B will also send out the wave at the same time. So like there's no lagging, or more precisely, there's no phase lag between the two sources. They will be in phase throughout the whole situation. And this is important to make the equation valid. Otherwise, if they are out of phase, that means they are lagging by 180 degree, or we can call it pi in radian, then these two equations would need to interchange. So constructive interference will be n plus half bracket lambda instead. But usually I would say it should be alright. So I guess you don't have to worry so much in IB physics. You may be wondering why there's no subtopic 4.5, because I also wonder the same thing. Okay, 4.5 is about stationary waves, and there are equations also. And I would say the important equations or concepts that you need to know is that we mentioned something called fundamental frequency or first harmonic frequency. We usually annotate it with F1, and if we have other or the next order of harmonics, then we can call it Fn, or like F2, F3, and so on. And so they have a relationship with the fundamental frequency, and that's why F1 is so important. That is multiplied with n. So for example, if F1 is, let's say 10 Hertz, then the next harmonic, second harmonic, is going to be 20 Hertz. Okay, third harmonic will be 30 Hertz simply. However, again, it's not really related to the equation, but then I think it's essential to recall, and you can also refer back to my video for details as well. That is in a case where it is too open or too closed system, alright, or open end or fixed end, then you have all harmonics. But then in the case where you have one opened, one closed end, then you only will have the odd number, okay, like this. And so this is something that we have deduced, and I guess I'm not going to explain why, but then this is something that you may want to pay attention. Alright, moving on to topic 5.1. The first one is current definition, nothing really special, charge over time. You should be okay with that. And then the next one is Coulomb's law, which is the electric force experienced by the two charges. So K is the Coulomb constant, and that could also be expressed as 1 over 4 pi epsilon log, which is permittivity of free space. So all these you can find from the earlier page again. Coulomb constant, permittivity of free space, and I would say usually just stick with K, I would say. And then Q1, Q2 is simply the charge in Coulomb, and R is the distance between them. The thing that I would remind you is more about not the calculation, but then it's more about when you state the definition. Sometimes they will ask you, or ask you in the MC, you need to recall that they are small point charges. Okay, so they don't take up space basically, and that's how you can find out the 2 point by R. The next one is the definition of voltage which is work done. That means energy over charge. So nothing really much to remind you, except sometimes they may use this is useful for converting from joule to electron volt. Okay, so you all would need to know about how to convert this, and the way to convert this is something to do with substituting Q with the elementary charge. So elementary charge is something you can find from here in the earlier pages. Okay, so this is how many coulomb for one charge. So 1E equals to 1.6 times 10 negative 19 coulomb. Very small, of course. The next one is electric field strength. So the F here is of course talking about electric force per charge. And so here again, nothing to do with the calculation, or you should be able to understand this. Of course, you shouldn't be mixing this up with energy. There's no way this is energy here. It's more about the definition once again, referring to, again, small point, but then this time, not just point charge, but also small point positive charges. Because you know the electric field will have a certain direction as well. It goes from positive to negative, and therefore if you have, let's say, a test charge as positive, then this test charge would be attracted to the negative side, and this is the force that it's experiencing, so it go along the electric field. While if you have a negative charge, it will have a force that is going opposite to the electric field. So that's why in the definition it's very important to also include the idea of positive. Okay, next one here is I equal to NAVQ. I is current, and N, if you look at this document, again with due all the respect, I appreciate the hard work, but then here I think is not precise enough, because N is called the density of charge carrier, but not charge. So here it should be number of charge carrier per unit volume. So an example could be simply the electrons in the space. So from, you can see the textbook as well, the numbers of electron per unit volume, or the so-called number density of free electrons, is N equals to 10 to the power of 28 per meter cube. So it's important to notice is the charge carrier. That means electron here. Electron is not the charge itself. Electron carry the charge, which is -1. And so here that will be N, and A is simply the cross-sectional area, and usually it is circle, and therefore if you have the R radius or diameter D, then you would need to use the equation, mathematics equation, which is also provided but not in this booklet, I think, because IB updated the booklet, and therefore you should have some mathematical equations about area and volume, and so just to make sure you are aware of that, okay, although it's not in this file. As for V, V is the drift velocity, talking about the mean or average speed that is moving along the wire, while Q is the actual charge. So again, if you're not really sure about how to use it, look at the example that you did, or this one. So the E is substitute, like the elementary charge is substitute into Q, which is 1.6 times 10 to the power of -19, and that's how you can mathematically calculate I. One thing that I would like to remind you more on the concepts here is N and Q, it will depend on the material, and most of the time in physics, we will be having the same material in the same question, because they probably would say, oh, in a wire they have changed the diameter, something like this, okay, and then obviously they are of the same materials, and therefore N and Q will be the same in this case. Of course, I'm not saying that always, right, because there's no absolute, I can't guarantee, and I don't know the question in the future as well, but then usually they are the same if they are the same material. And the other thing that you should be aware of is that current is going to be the same. So if this is I1, this is I2, and in fact they would be equal, because you can simply consider they are just a series circuit having two resistors here, so the current must be conserved here. And before we move on, I would like to remind you and also another important concept, that is for potential difference, this is scalar. Okay, so that means you don't have to care about the direction. As for electric field or the electric force, they are vector. So that means when you're trying to add things together, you may need to consider the trigonometry. In 5.2, first of all, we have the Curtis first law and second law, and for this one, it's not really about the equation itself, it's more about how to use it. So once again, if you don't know how, you may want to refer to my video in 5.2. However, I would say the questions in IB Physics wouldn't be as hard as the one that I provide, because it might get too mathematically tedious. So in IB, I think the physics wouldn't want you to get to that point. So it's more about asking you the concepts. Next one is the resistance. This is a definition and also the name called Ohm's law. One thing that, again, to remind you, is it is not dV over di. Alright, it's not instantaneous, and therefore whenever you have a graph of, say, V against I, and no matter what shape it is, okay, I just randomly draw, you are not looking at the instantaneous slope. Okay, you should never look into that, or this one. What you should do is probably finding out this origin, draw a line to it, because this is V and this is I simply. So always draw the line from the origin and use that gradient to find out the respective resistance. Next up is the power for the circuit. So I'm sure you all know how to use it, but just again, one thing that people usually make mistake on is the V. V is potential difference. Okay, it's how much it drop, not how much you have in total, because sometimes in the circuit you may have voltage for first component, second component, third component, and in total when they add up together it will be the EMF. And so if you really want to use this equation involving V, making sure that it is really the potential difference of the component that you are calculating, so that power or that resistor of that particular component. Or if you're doing for the whole circuit, then make sure all these are for the whole circuit. And moving on, for these two equations, I think it's very obvious and you all should know very well. Just one thing to again give you as a tips is for parallel, if you have a circuit, parallel circuit that is the same resistor, let's say this is R, this is R, this is R. Alright, and if you want to find the equivalent resistance of them, again, if they are all of the same resistance, then the trick is it will just be divided by the number of resistor you have. So here will be R over 3. This is something that you can derive mathematically. And this trick may sometimes help you to save time during the MC. However, in long question, I'll recommend you to show the steps and tell people how you obtain this answer. And for the last question here is usually I will phrase it as R equals to rho L over A. If you like to do this way, that's fine as well, as long as you know what they are. So rho is not density, it's something called resistivity depending on material. A is area, so the cross-sectional area. So usually again it is circle area. And then L is simply the length. Alright, so in 5.2, something much more challenging and people usually miss out is something called the potential divider. So once again, if you have no idea what it is, I will recommend you refer back to the video, which I can explain in details. But then the basic idea is if you have, say, two resistor R1, R2, and they are connected with a battery that is of epsilon EMF. I mean, this is not potential divider, but then there is an equation that is usually related to this. That is the V1. Let's say this is taking up V1, this is taking up V2. Then V1 equals to epsilon over the total resistance. Okay, as this fraction R1 over R1 plus R2. So this is total, and R1 is how much you get. So this equation usually is quite useful when you are solving potential divider questions. And of course, a picture of potential divider is something like this, having a contact point where you can adjust. And again, for more details, I think you should refer back to the video that I made earlier. Next one is simply about cell, considering the internal resistance as well. So this is the equation. Epsilon, this is EMF, and big R is outside, the equivalent resistance outside of the circuit. Small r is obviously the internal resistance. One concept that you should recall, again, nothing to do with the equation, however, you should definitely know that if you try to plot the graph of these, I believe this should be V against I, and then you should have the slope to be negative small r, and while the y-intercept is going to be the EMF. Topic 5.4. So this is the magnetic force experienced by the charge. So Q is a charge in coulomb, V is the speed that is moving, and B is the strength of the magnetic field. And then you may notice here is a sine theta again. Ideally, if you recall by hand rules, left hand rule or right hand rule, no matter what, it's always 90 degree. So that means the force, that means FBI actually, like if you look at the left hand rule, they should be 90 degrees to each other, perpendicular to each other. So in case if they don't, if they have a certain angle is instead, then you should take the sine theta. Again, you should be able to judge whether it's sine theta or cosine theta by looking at the diagram provided by the question. The next one is similar, where we have magnetic force induced equals to strength of magnetic field times the currents times the length of the wire. Notice that this is a strict wire. Alright, of course if it's curved, then you don't know how to deal with it, obviously. And then again, you have to make sure that the angle are 90 degrees. If not, you have to multiply sine theta. And just a tip for you, usually when you are doing a question like this, it may involve a circular motion, so that may relate to chapter 6 later on. Another concept that I would like to remind you here before we moving on to chapter 6 is that electron movement, alright, as most of you would know, is the opposite of the conventional current direction. So when you are using your hand rules, you want to make sure that you can recall this. They are opposite. Alright, moving on to chapter 6.1. You can see these are the three equations and the names of them. So sometimes you may also need a very simple one, that is period equals to 1 over f. Actually, these appear in ways earlier. Another thing that you may need to know is V is the velocity, or more precisely is a linear velocity. R is the is the radius, sorry. Omega is the angular velocity. And in fact, this is combining and deriving equation between them. V, linear velocity, has a definition in circular motion that is 2 pi r, which is the circumference of the circle divided by the time period you need. So that obviously is simply how much you run divided by the time that it takes. So this is linear velocity. While for omega, sorry I didn't write very well, this is V, not R. For omega, it's going to be 2 pi only, because 2 pi in radian is one circle, 360 degrees. And if it's divided by t again, these two are the definitions of linear velocity and angular velocity. And if you put them together, then that's how you get this equation. As for the other two equations here, A here is the centripetal acceleration. I usually annotate with AC down below, and F here is referring to the centripetal force, FC, I annotate usually. And for the centripetal acceleration, there are actually 4 forms, like 4 transformation or 4 variants of expression. So the usual one you use is V squared over R. Okay, I call it 1. And then here you can see there's another one called number 2. And then you may find this one is the same, right? So ignore that. You have the third form here. Okay, and if you're wondering like where is the fourth, then you can actually transform it from number 2. That will become 4 pi square R frequency square, cause using this equation to derive. Although I would say most of the time using the first form will be enough. Next topic, we have the gravitational law. Again, I'm sure you all know G is a constant that you can find earlier. And again, the thing is about when you write the definition, the M has to be small point mass, okay, similar to the Coulomb's law. While for the gravitational field strength is the gravitational force divided by mass, how much force per unit mass. So again, you should be pointing out that is small point mass. And so this equation is simply by substituting the F into this, and then you can get this. And obviously for 6.2, you should recall it's very often that you will have this gravitational force to maintain the circular motion. So you probably would want to link this force with maybe mv squared over r, or changing this to something else, because obviously this is based on F equals ma simply. So choosing your own centripetal acceleration, and then this centripetal force will simply be the gravitational force. For chapter 7, I think it's pretty self-explanatory, so I'll just go through it quickly. So the first one, E, is the energy when you have the electron go from one level to another level, or you want to get the energy to go from a lower one to a higher one, and that's the energy you need. So more precisely, I may call it delta E, and that is the energy of the photon being emitted or absorbed. So H will be the Planck constant, which again you can find from the previous page right here. And F is the frequency. As for the second equation, is in fact the same if you are looking into C equals to F lambda, the wave equation, and if you substitute, it's the same equation as the first one. And that is pretty much the equation you have. For 7.2 is the very well-known Einstein equation, E equals to mc squared. So as you all know, E is energy released, mass, M is a mass defect more precisely, so not just mass defect. And then for C is simply the speed of light. So you should be able to work out the mass defect, and the mass defect is the difference of mass between when they are all put together and they are all separated for all the nucleons. 7.3, I think again is very obvious. You can see all the names of the quarks, and you just have to pay attention about the strangeness. So for a strange quark is -1, not positive, or it's -1 first, while for anti-strange, its strangeness is +1 instead. Again, don't ask me why. I mean, this is decided by the scientists before. While for leptons, you can see these are the names. I'm not going to repeat it, but then this is the reason why you find out for beta minus, you will have anti-electron neutrino, while for beta plus, you will have the electron neutrino. Oh, I just recall back to earlier, 7.2, there is a graph that definitely you need. This is called the binding energy per nucleon number, and then this is the nucleon number, simply. So that's one of the graphs that you definitely need to study, and also you also need to know how to calculate, if they have given you maybe some sort of numbers, how to calculate the binding energy per nucleon number. So basically it's using this equation, E equals to mc squared, but then remember to divide the nucleon number afterwards. Chapter 8.1, we have this equation which is super useless. I mean, we all know about this already. Before we talk about the next one, I would like to talk about the two keywords that, or terminology, you need to be aware of. One is called the specific energy. One is called the energy density. Okay, definitely two terminology you have to explain clearly or understand for calculation. And the way that I recommend you to memorize it, again, that was mentioned in the video earlier. Specific energy is similar idea. I mean, the word specific is the same as specific heat capacity. So this is how much joule per kg, right? Same as specific heat capacity versus heat capacity. It just depends on whether it is per unit mass or not. Well, for energy density, it is of course joule per something, right? Because if you recall, the usual density is rho equals to mass over volume. So it's divide volume. So here is also divide volume, that is meter cube. So using this, you can obviously go back, like backward engineering, to work out the equation yourself easily without mistake. Before we're moving on to the next equation, I want to talk about hydroelectric. So for hydroelectric, it's not something about the equation itself, it's about when you are expressing them. So let's say here is a very simple wall, okay, with water inside, and then it will flow down with a tube, let's say, and there's a generator. Okay, I'm not going to draw it, just write G, okay. And then you may find here is a big H, and here let's say it's a small h, representing the height of the water. And so you need to be very careful about the energy expression that we are having. Well, we all know this is GPE, while the expression in general is mgh, but then the h here, you need to be very careful, because other than just the big H, because this is how much it dropped in height, you also have to think about the height of the water as well, unless the question simplify it. But then usually you have to think about it, and that is the half of the water. The way you can think about it is you can kind of treat this as the center of mass, and so you also have the small h over 2 to add up when you calculate the GPE. Alright, so back to the second equation, you see here is that power, but then you should know this is referring to wind power, and that is the equation half A, which is the area of the blade, rho is the air density, and then V is the wind speed, okay, to the power of 3. And so the assumption of this equation was widely discussed in the video and also in the syllabus, so I'm not going to repeat it, but then one really key ideas, okay, I'm repeating it, is the wind would not stop after the turbine. So that means the KE will not be fully obtained by the wind turbine. But then this equation is assuming that. So in theory, not in theory, I should say in practice, the power should always be smaller than this. So because of this, sometimes the question may ask you to find out the actual power or actual KE that you obtain from the wind turbine, and this is something similar to the elastic potential energy I mentioned earlier, because of the mathematical formula here is to the power of 3. So what you can not do is if you try to simply use V1 minus V2, this is definitely a terrible idea. So what you want to do is to separate them, right? Calculate them separately. So like V2 to the power of 3, and then you also minus this. Okay, and of course, I mean, if you are mathematically sensible or conscious, then you could, all right, given that other things doesn't change, then you could do something like a bracket minus V1 cube. So this cube minus this cube. So don't put the cube outside because it's just not equivalent. Okay, finally we get to topic 8.2. So the first one is about power P, okay, about the radiation more precisely, and that is E sigma A T to the power of 4. So this is something that you would surely want to make sure you know what they are. E is emissivity, and the sigma is called the Stefan-Boltzmann constant, which you can find here. And for A you may think, oh, area, but then this is something that people sometimes get confused with. This is the surface area of the body. So the body usually is modeled as a sphere, and therefore again this area you can refer back to the surface area of a sphere equation, which usually you will be using 4 pi r squared to calculate. While for T is the temperature, and make sure it is in Kelvin. In fact, I don't know why the second equation they reminded you what unit you use, but then like, why is this an exception? Why not provide the unit in the other equation as well? But anyway, the temperature here must be Kelvin. The other thing that you should be aware of is that this equation actually calculate the power radiated by a body and also the radiation power received by a body also. So if you really want to find the net power, then you want to find the expression to be E sigma A T2 to the power 4 minus T1 to the power 4. Again, similar to the one for wind turbine, you will put the index inside. So one is emitting, one is absorbing. The second equation is about Wien's displacement law. So in case you don't remember, it's something to do with the graph of different temperature. So you have intensity here, you have the wavelength here, then you always find there is a shape something like this, and then there is a certain lambda. That's why we call it lambda max, because it has the maximum intensity. And then for this particular temperature, right? Temperature is not shown on the graph, but then it's more like stated by the question. And so yeah, they simply have such a relationship. 2.9, this one is more like a constant simply. For the third equation here, I apparently have mentioned it in waves. I would rather say the more important thing that you should pay attention to is when we try to derive the solar constant, we are actually using the idea of 2D plane, okay, because the solar radiation, when it comes to the Earth, you would have the area of a disk, okay, of a 2D circular plane to receive it, and then it got shared by the spherical area. So if you look at the derived work here, that is why we have such an equation, and when we substitute the relevant number into it, then that's how you get the average intensity on Earth. So I would say the way that you derive this would be important, and it might, it actually happened before. So I recommend you to understand how to derive, right? Memorizing this equation is useless. It's more about knowing how to derive. Lastly, you can see albedo here. The symbol is usually alpha, and I don't think I have to explain much here because these are the wordings given to you already. The idea of total scatter power, you can also see it more like the reflection as well. So how much is being reflected over how much it is being sent, at the first place, so the incident power. Okay, so I think that is all for the video, and I hope you have already mastered these three things for each topic from 1 to 8. Again, there is no guarantee that just now the video cover all the concepts. Remember, we just go through the equations only. However, there are some concepts you should refer back to the list of the syllabus, and those cannot be described by equations simply sometimes. So for example, for each question set booklet I made, I have copied the official guideline, and so these are the terms and also the concept statement you want to refer to. And so if you go through the whole list of all the topics, then you should be good to go. And so after watching this video, one thing that I would recommend you to do is, if you have a printer, print out a blank data booklet and try to do the dictation. Okay, I'm not even joking. Do the dictation and just try to write basically all these things out, including the names of the variables, and that will be very useful, and at least make sure you know the very basic stuff of the exam. If you find this video useful, please hit the like button, leave a comment, and share that to your friends. And if you are looking for the HL topic, please let me know as well, and I will think about making another one for the HL topics.